Hi, my name is Michael Tastian, and today we're going to talk about pumping lemma for regular languages. So, first, what is a regular language? A language is regular if some finite automaton recognizes it. But really, what does that even mean? Well, recognizes means the automaton M accepts exactly the strings in the language L of M equals A. And every string in A is accepted, and every string it accepts is in A. So here's a quick little refresher. L equals a language, M equals a machine, A equals L to the M. In plain English means the language A equals the set of strings recognized by machine M. So, moving on. The pumping lemma is a property that every regular language must have. We use it in reverse. So if a language fails the property, it can't be regular. So let's assume a DFA has fixed number of states, M. There's a string, and the length of that string is greater than or equal to M. M plus 1 states are visited, so there must be a repeat, which is the pigeonhole principle. And between the two visits to that repeated state, the machine ran a loop. The substring that ran in that loop is the pumpable part. As you can see here, I've put a little note here. Now, formally, we can say if L is regular, there is a pumping length M such that every string that's a part of L with the length of that string greater than or equal to M can be written and broken down as S equals UVW, where V cannot be empty, the pump piece sits within first M symbols, and for U, V to the N, W is part of L for every N greater than or equal to 0. Basically, pumping keeps you in the language. Here, you can kind of see that I've sectioned off the pumping part. We're kind of forcing it into the UV part of UVW. So, here's our strategy again. It's how we're going to prove a language is irregular. We're going to assume L is regular. So pumping lemma exists. We're going to choose a specific string. Then we're going to split up S. Then we're going to choose N. N equals 0 means we're going to pump down. N equals 2 means we're going to pump up. And then we're also going to show that U, V to the N, W is not a part of L, which contradicts rule 3. Thus, L will not be regular. We're going to choose S in a way so that, again, we isolate V in that one block of symbols. And the pumping will change that block's count, breaking the required relationship, which we will show here with this problem. Simply put, we've got a language where there's some A's, some B's, some C's in that order, with exactly one more A than C. Pretty easy. Suppose L is regular. Then L equals M of L for some DFA M with M states, as we said earlier. Now here's our constraint. We've got I equals K plus 1. So the number of A's equals the number of C's plus 1. So we can say that S equals A to the M plus 1, B to the 1, which is just B, and then C to the M. Written in terms of K, that's A to the K plus 1, B, C to the K. And now we're going to say a string is in the language since A, M plus 1, B, C to the M follows the supposed requirements, where the length of S equals M plus 1 plus M, which then equals 2M plus 2, which is greater than or equal to M. Now we're going to break apart S. S equals UVW, where V is not empty, and the length of UV is less than or equal to M. And UV to the N, W, is a part of L for all N greater than or equal to 0. So, A to the M plus 1 means the first M symbols are all A's. The length of UV less than or equal to M means V is all A's. So if we say V is equal to a to the t with t between 1 and m, then if we pump down where n equals equal to 0, u v to the 0 w will then just equal uw, which can be written as a to the m plus 1 minus t. And because a to the m plus 1 minus t, b, c to the m, and t is between 1 and m, I equals k plus 1 cannot be true by the pumping lemma with n equals 0. I hope that all made sense, and as a bonus, I've included a picture of my cat here. Thank you.